All right, week 4, we spent the first 3 weeks. Week 1 was material properties, densities, viscosities, interfacial tensions. Weeks 2 and 3, we were first talking about fluid pressures at a point for week 2, which rely on the fluids around it and above it, typically above it only, which allows us to be able to calculate fluid pressure as a point. And then we spent week 3 talking about how to integrate that over length to be able to get the forces that act on structures, which is important in being able to understand whether structures fail. This is really the role of that. All of that has been to do with, actually it's not very impressive this, is it? All of that has been to do with fluids which are so-called static, which means that within a beaker, you could imagine, there's no circulation. And we've come up with some rules that say something about the behavior when that truly is the case. But we also said when we began talking about static fluids at the beginning of week 2, that we could not necessarily restrict it to fluids which are physically static, but also fluids which are in a beaker but are non-circulating. So if I take a beaker, and if I run, I'll try and keep on recording on this. If I run across the room with a beaker in my hand that has fluid in it, then that's not circulating. It's static, even though it's moving across the room. And so we never really said it, but if fluids are moving at constant velocity, it doesn't really matter to us. We can treat them as static fluids. But if they're accelerating, so if I run with this and accelerate across here rather than moving at constant velocity, then, let me go back again, then we can also treat accelerating fluids as being quote-unquote static. And we know that fluids moving at a constant velocity behave exactly the same as fluids which are static. And the reason we know that is because we're not static on this planet. So we go around once a day to be able to have the diurnal variation in light. And so it's 20,000 kilometers around the circumference of the Earth, one day, 20 hours. So 1,000 kilometers an hour is the velocity we're moving at now going around the axis of the Earth. I think if it's 93 million miles from the sun, and we go around that in a year, so that's 600 million miles in a year, 300 days, then we're going something like 2 million miles a day, which is our velocity now. And so clearly we're moving at some velocity, but we're not really accelerating. And so that's the key. So everything that we've done so far, we can think of as being static fluids or moving at a velocity. And now we're going to make a departure from that by looking at fluids which are accelerating. So one example of this is here. It's an earthquake. It's not really a steady state problem. So the ground's being pushed backwards and forwards, probably far from an earthquake. The period of oscillation might be 20 seconds or something like that. And so the fluid is being kind of excited and moved backwards and forwards in this sesh within this lake to be able to deal with that. So that's kind of what we're talking about. It's being accelerated, but it's not steady state. And actually, it's not a very easy problem for us to analyze. But the essence of what we are dealing with is shown in this example here, which actually was sent to me by one of your predecessors, one of the students in class. And it's a piece of double glazed glass within a bus that has water that's leaked into it, which is this big black horizontal line that's there. And as the bus accelerates, something happens to that. And you can imagine it that if you're pushing snow with a bulldozer, it's not quite the same, but stuff mounts up against the bucket of the bulldozer. And so you could imagine if I'm running across the front of the auditorium like a crazy guy, accelerating, that the stuff would pile up at the back of this container that I have because it's being accelerated, just like it's happening. So you see that when it accelerates forwards, it stacks up at the back. When it decelerates, it piles up at the front. And so there's some process in here that's controlling that's acceleration. So it may seem a little esoteric in terms of looking at it, but we will try and analyze that situation. I'm trying to think whether we did talk about this when we first met, and I don't know if you can see this. If you look at railroad, maybe you can see it. Let's go full screen. No, perhaps not. But if you look at these cars, if you look at the design of them, the filling point is depressed compared to the ends. And so I'm guessing, I don't know if that's the case, but the idea is that when these railroad cars accelerate, then the stuff gets pushed up at the back, and if you don't want that change in water level to pop the cap that's sitting on top of it that seals it, then you have some extra airspace both at the back and the front of it. Likewise, I suppose starting isn't such a big problem because a heavy train can't start very quickly, but it can try and stop very quickly. So you have the opposite effect. If you stop, if you're going left to right and you stop, then the fluid in this would tend to pile up here. And so that's basically the problem that we'll deal with today. The other thing that it impinges on is that we'd also be interested in this as a form of acceleration in terms of how a centrifugal or a centripetal pump works. And the basic idea is that if you want to pump things, one way to do it is to have a turbine that takes the fluid and flings it out to the edge as it spins around. And if it does that, it's providing some centripetal acceleration to it as it goes around. And as it throws it out, something has to fill the space that it's left. And what fills the space that it's left is the stuff that flows along the length of it into the pipe to fill that space. So centrifugal pumps are another manifestation of kind of flowing fluids, which we can also think of as static fluids in their simplest incarnation. So that's kind of where we are. And we'll also use what we're talking about today to be able to say something about, from static fluids and accelerating static fluids, that is the essence of the Bernoulli equation. So it moves directly into that. So the work that we've done so far, that we've worked very hard on to be able to get to where we are in this class, we can actually use to be able to pull out of our hat, if you like, the Bernoulli equation. So that's our plan for the day. Okay? So I won't go back and retread what we talked about in terms of statics, but I will maybe revisit the expressions that we talked about. So we bit the bullet in class 2.1, and biting that bullet was to derive this expression here, which we only used a part of. We've always so far assumed that accelerations are zero. And so this expression that we had before, which is a longer expression, which is really, if I divide it up about this point here and paraphrase it, this is basically what that expression is. These two components on the left, dP, dx or y, and the unit weights of the fluid are forces in the system. And these are parts that are due to acceleration. If, for instance, we divide these through by volume, not velocity, but volume, then by definition, this term that we have here is density. And so density times acceleration is exactly the term that we have here. So the expression that we used when we assumed that all of these terms, the accelerations are zero, and it reduced to two important expressions. One was that as you go horizontally in a fluid to another point, you have to be at the same fluid pressure because there's no pressure change if you don't change elevation, which is what this is saying, which came out of these two, this expression here, written in longhand. And the second one, which we've used much more usefully, is that if you go up and down in a fluid, then at least in a fluid where it's constant pressure, or constant density rather, then the pressure is equal to something like this. And we've used this expression. And this expression comes directly out of integrating this when density is constant. But we've thrown away the acceleration terms. By definition, since we can make this right-hand term look the same as these here, these have to be the same units as this dp dz term. And so we can think of this change in pressure with elevation, or this differential, just as a force per unit volume, because that's exactly what the units are here. And of course we know that that's the case, right? Because we know that the change in pressure with elevation, which is equal to minus unit weight, is in units of newtons per meter cubed, which is exactly the right terms for this, right? So that's where we're going with this. So what we'll do today is we're going to ease those restrictions. Did I dim the lights as I wanted to? I think I did, right? So we're going to ease those restrictions, and we're not going to make this assumption that the accelerations have to be zero. And so if we do that, we can do a couple of things. So we'll at least play around with, we'll look at two situations. One is linear accelerations in a straight line, me running across the front of the class. The second one is rotational accelerations, where we're spinning something at a constant rate, but because velocity or acceleration is a function of not just of the speed but also direction, then clearly the weight on the end of that string might be going at the same speed in an arc as it goes around, but it's accelerating because it's changing direction at every stage as it goes around, as it spins around, right? Changing physical direction as it goes around. So those are the two things that we'll look at. So the first one is linear acceleration. And here's the basic idea. I am on the screen, good. So imagine we have a bucket. We know that in that bucket, if we have a fluid, that it would sit here. We know that we have a reference frame which we've defined, which is, I'll call y and z. We know that z is positive upwards. We know that for that coordinate system, x, y, z, x is physically into the board, just from the right-handed coordinate system. And we can surmise, we know that gravity is acting downwards. And what we'd like to be able to do is, for instance, be able to apply some acceleration in the y direction to this. From everything that we could imagine, maybe, we might think that the fluid level would look like this, from what we've said. And maybe there's a couple of things that we'd like to be able to figure out. One is, what is the elevation change of this surface? And I suppose the second might be, what is the fluid pressure distribution that we then have on the back of this container as we look at it. So those are the two things that we'd like to do. So the first is inclination of the free surface. What is it? So what we could do, if I can just scoot that down, is we could go back to these expressions and remind ourselves of them. What we're going to do is now we're going to allow these to be non-zero. And so if we do that, then if I write this out, we end up with, for these expressions, change in pressure with x is equal to minus density times the acceleration in the x direction. So in other words, this term here, this is a negative, this is a 0, this is a ax rho. So I'm just pulling it off this. Maybe I'll make this smaller so you can see both at the same time. If we look at pressures in the y direction, it's just a permutation of that. This is density, this is pressure. I know they look a little similar. And if you look at the one that we've used so far, all of a sudden that, if I can move it up, ends up being change in pressure with elevation in the z direction is equal to minus, let's write this out as rho g. Acceleration z direction. So this is just this term here, right? So those are the three expressions that we get. And so we have this container that we're going to want to accelerate from left to right. It is still left to right for you as well. We keep the coordinate frame. Still on there? Okay. So what could we do? What we could do is we could say that we could look at the change in pressure as we go along this surface. And we know that the pressure here is atmospheric, and here, and here. And so perhaps what we could do is we could put this equal to 0 and try and solve to figure out exactly what this inclination is. So we want to determine what d z dy is. Is that still on? Yes. So what we could do is we could write this expression, the change in pressure is equal to the change in pressure. Hopefully you believe me with that. We could multiply that by 1. Hopefully you'll believe that. We could add to that a change in pressure, which we again multiply by 1. And we can finally add a pressure, dP, which again we multiply by 1. So these are just ones, so that's fine. But you could argue, I suppose, that we have the change in pressure is equal to 3 times dP. But they're not, right? Because they're all orthogonal. So as you move in one orthogonal direction, the other ones are independent of that. That's the one kind of condition of orthogonality, if you like. That's why we resolve in x and y directions, because the forces in the x direction have no impact of the forces in the y direction. And so if we believe this, then in this particular geometry, the acceleration in the x direction, which is out of the page, is 0. So in other words, the acceleration in this particular case is a bucket that's accelerating this way, not moving at constant velocity, but accelerating. And so if that's the case, then let's use a different color. This, by definition, is 0, because this is 0, and therefore this is 0. This term here, dP dy, is this, which is not 0. And this term here, dP dz, is this term here. And so if we gather terms and we write it out, then this is 0 minus rho acceleration in the y direction dy minus rho acceleration due to gravity plus acceleration in the z direction times dz. And so we said we wanted to get this. We have both of these terms here, so we can gather terms. We know that the pressure change along this boundary is 0. And so if we put these two terms together and come up with the final solution for that, then it's going to be the change in elevation as you go horizontally is going to be equal to densities drop out, acceleration in the y direction divided by gravity plus acceleration in the z direction. And one comes to the other side, so there's a minus sign in this. And so physically, if we look at this surface, that's probably off the page. Physically, if we look at the surface that you have in this bucket, then that's exactly what you have here. So this is dy, this is dz, and that's exactly what this expression is. And so the bus case that we had a little while earlier accelerates, it goes up some amount. It certainly didn't go to 45 degrees. Maybe it went to half of that. I would say this is maybe, this was 1 to 2. And so if this is acceleration due to gravity, which is 9.81 meters second squared, plus acceleration in the z direction. Well, the bus was pretty much going on a horizontal road, so there is no acceleration in the z direction. And therefore, the amount that must be on the top must be something like 4.9. Just because of this, right? So it's kind of interesting. So you can get some idea of the acceleration of that system merely from looking at the magnitude of the inclination of that surface. So as you go faster, or you accelerate faster, then it will be more inclined, and therefore it will climb up higher on the back of the window. And I suppose we haven't really talked about it yet, but I was very careful when I drew this to rotate this around this point here. Clearly there's kind of a conservation of volume issue, right? If you have the level here and it goes up at the back, then it has to go down at the front to compensate. And so just from conserving volume under this, the area that's under this curve here would be roughly the same as the area under this curve here. And so there's some conservation. So kind of interesting that we can get it relatively straightforwardly out of that. Okay? So we can always, so we've done at least one of the things that we wanted to do. We wanted to get the inclination of that free surface, and we have that. The other thing that we said we'd like to do is that once it's crawled up the side of this container, what's this pressure distribution that we have? Is it equal to what we said before? That it's equal to, we can index it as an incompressible fluid proportional to depth. Well, it's not going to be, right? We can see that straight away. And we can do that by merely looking at one of these terms here. And if we take this last term here, this expression really was born out of this term when this was the only thing that's here. What we've done is we've added an extra term to it. And so what we could think about is that instead of this being equal to minus unit weight, because that would be the case if it was only these two terms here, that it's actually equal to some kind of surrogate unit weight, which is increased by some acceleration. And so we don't have to think too hard to be able to realize that if we looked at the surface of a fluid, is that still on the screen? Yes. And we went down in that fluid, that if the pressure change with elevation is equal to gravity plus some amount, then all that's going to happen is that it's going to increase the magnitude of that pressure. So if this was the case where AZ is equal to 0, in which case P is equal to P0 plus unit weight times H, right? And I should label these, right? This is minus Z. This is positive pressure. This, I suppose, is plus Z. Remember that our sign convention is always, and we'll have to be a bit more rigorous about that now when we move into Bernoulli, that z is always positive upwards. I wrote it in terms of h just because it's convenient to do that. But if there's this additional component that's added to it, then if we're accelerating upwards and if the z acceleration is positive, then it's going to look like this. Az positive. That's my, remember that's my notation for positive. And in that particular case, the pressure is going to be equal to P0 plus rho plus Az times H. And this is H here, right? And of course, it makes perfect sense, right? So you can imagine, you know that when you go up in an elevator, you're holding your cocktail in your hand, that you feel in your ankles when you accelerate upwards, you feel a force because you're pushed down into your shoes. And that's exactly it's basically increasing the effective gravity that you feel. And so you would have a greater weight. Your mass would be the same, but your weight would be larger because you're accelerating upwards. And so this happens to be the rate at which that would happen. The fluid pressure in your cocktail would change as it goes to the bottom of the container. And when you decelerate at the top of your ride, then this would be where Ez is negative. Getting it a bit clogged, but it's useful to have it. What's it doing? Didn't want to do that. Az is negative. Right? Same thing. So you stop, and all of a sudden you feel lighter, and so does the fluid in your body. Most of our body is fluid. Blood and tissue are mainly fluids, and you feel lighter. And so we can get the pressures acting on the side. So if we wanted to calculate, so remember this is going up or down. So this is how pressure changes. It's slightly different from the magnitude here, where in this particular tank, if we're moving on rollers, we didn't say it, but let's assume that the acceleration in the z direction is equal to 0. So in other words, this is a truck moving on trundling on rollers, then the acceleration vertically is 0. So if that's the case, then if the acceleration is 0, this pressure distribution, even though it's piled up at the back of the truck, has to be just the same as if we're going down in a swimming pool that wasn't moving. And so the two things that have come out of this, I think, are one, that we can always get the slope of the free surface if it's allowed to realign itself from an expression that looks like this. And once we have this slope, we can get the pressure that acts both on the front and the back of this container. And the pressure distributions, if it's not accelerating in the z direction, will be just the same as if it's in a static pool. It'll just be that it's a smaller force at the front because this trapezoid, this triangular distribution, only starts at the free surface and then goes down linearly at this rate here from there. And at the back it goes down from a higher level and goes down. So the pressures, clearly if you look at the pressures along the base of this, there's some kind of gradient. And that gradient really reflects the fact that this inclined surface is inclined. So hopefully it's relatively logical. So the two things we wanted to do. One is the inclination of the surface, and also how pressures change as we go up and down in the fluid. If there's no extra acceleration over gravity in the z direction, then it will always be just a swimming pool distribution, and we can always use an expression like this. But if it is being accelerated vertically upwards or decelerated vertically upwards, then we can get the accelerations from that. Okay? Exciting stuff, isn't it? Yeah, fine. Okay, so, well, if you want, you can go through this and look at all the stuff that we have. This basically staying the same things. So those are the two things. So we can get the distribution, and we can also get the free surface. So maybe a little more challenging than that is to now think about rotations of fluids. And why not go back to it, just to make the case for what we had before. It's a bit of a juvenile example, but not this one, but what we'll use in a second. And that is that one of the other reasons that we'd be interested in accelerating fluid is that fluid is being flung out to the side in this case. It's being gathered in this trough and it's going off here. And the act of flinging it out to the side is the mechanism by which it sucks in new fluid along the pipe to be able to run. So centrifugal pump. And so it's kind of an important feature. And so this is a bit juvenile, but let me play this anyway, just because.
Hey, hi, I'm Chris, and welcome to So Cool Science. Science you can do right at home. I'm just hanging out on a planet in a solar-centric system and going over today's science file. And today's science, to So Cool Science. Science you can do right at home. I'm just hanging out on a planet in a solar-centric system and going over today's science file. And today's science file, it says, why don't the planets get pulled directly into the sun? Well, that's a wicked awesome question. Try this. You will need a mug, some ribbon, a plastic tube, and a spool. Start by getting yourself that mug and some ribbon. You're going to tie a few knots around the handle of the mug to secure it in place. Now thread the ribbon through the plastic tube and through the spool as well. Now tie a couple of knots in the ribbon to secure the spool to the ribbon. Now check this out. The mug is definitely heavier than the spool. Now here's what you're going to do. You're going to give the spool a spin, a lot like this. That's so wicked cool. Now, that's pretty wicked cool, but this is the So Cool Science Show, and I gotta blow your mind. Not literally. I'm not literally, gonna blow your mind. Check this out.
So that's probably enough. So, it's an interesting demonstration. You can imagine that thing that you're swinging around a head being, for instance, a piece of Tygon tube which has fluid in it, which would want to shoot out of the end. And so that's probably closest to the analogy that we're interested in. But for now, the basic question we have is if we're looking at rotational accelerations. So I guess that's our next thing, is rotational accelerations. And so I used to derive this, but I'm not sure that we really need to. But the idea is if we have a lever arm with some radius to it, and something is moving at some velocity that we'll call v theta, and it's moving around this fulcrum here, and this fulcrum has our z-axis vertically. So z-axis vertically, radial axis horizontal, radially outwards, and a tangential axis theta. So this is the r-axis, this is the z-axis, and this is the theta axis. Then as this spins round by some amount theta, then what happens is that this velocity has to deviate some amount theta from its straight direction. We know that if something is moving in a straight direction, Newton says if it's not acted on by anything, it'll just keep on going and going and going in that straight direction. But if you want to physically move it in another direction, then you have to apply some force to it. And of course, the force that's applied to that is this centripetal force, F, which is applied to pull it in here. And so the idea is that even though it's going around at a constant rate, so it might be going around at omega radians per second, omega is the term we'll use, even though it's going around at 1 revolution a second or 1 revolution a minute and stays that, because its speed is still the same, its velocity isn't the same because it's changing direction all the time as it moves through this angle here. And so what we could do is we could write out that force is equal to mass times angular acceleration, in this particular case. And we can write angular acceleration as just v theta squared over r, I think. Yep. And then if we do as we did before, we divide both sides through by a volume. Then we said that by definition, this is the units of dp dz. And in our particular case, this is just going to be change in pressure with radius. And we can write this, as you'll see, as it's written below, is that change in pressure with radius is equal to rho. It's okay. So mass divided by volume is just density. And v squared over r. And if we note that the velocity v theta is equal to the radius multiplied by the rotation speed in radians, we can substitute that for this expression here, and we end up with rho r squared omega squared over r, which is equal to rho r omega squared. So hopefully not too painful to do that. And if you look 2 lines below, of course, you'll see exactly that term as a standard result. So it comes really just from F equals ma, swinging something on a cable. It's going at the same speed, but it's changing orientation, so there's an angular acceleration. This angular acceleration we can write in terms of its rotational velocity, and if we just play around a little bit else otherwise, so these two go out, then we end up with this. So these end up being the rotational equations for a rotating fluid. And so you can imagine the similar behavior if you like carny folk, and you go to the carnival and you go on the machine where you spin around, then the floor drops out from underneath you, you get plastered against the wall. And so you can imagine that if you find fluid present within a container, then you get exactly the same thing. The fluid, just like accelerating it, is going to be pushed out into the walls. And so we can use that to do the same derivation that we had before. And that would be that 2 things we'd like to know. What is the shape of that surface? And what is the pressure distribution as we go down through the walls? So those are the 2 things that conceivably we'd like to be able to do. And so the first one, we knew how we did it. We took the fact that the pressure change as you go along this surface has to be equal to 0. And so this is 0. And we can write it in terms of taking, remember, getting rid of these terms. dp plus dp plus dp equals dp is what we did before. And so now we could just substitute these expressions in here. This one here. This one here. Whoops. And this one here. And so if we do that and rearrange with this 0, well, maybe it's actually worthwhile rationalizing what these physically mean. So this says that the pressure change as we go radially outwards varies with radius. And so that means that you could think of the pressure change really as being a surrogate for the elevation of this surface. Not quite, but it's really saying that as you move along the base of this container, the pressure change here as you go horizontally is 0 because radius is 0. This is the radius. As you go further out, then radius increases, so the pressure change would increase. And so I guess the pressure change would look something like this as you go outwards, right? It's proportional, the gradient is proportional to radius, but then this is actually the magnitude of the pressure, not the gradient. So we know that in the middle it needs to be 0. If you go vertically down in this fluid, so long as it's not accelerating upwards, then the pressure distribution would just be the same as in a swimming pool. If it was accelerating upwards, then I suppose we'd have to just modify this to include this AZ term going upwards. So I guess these relationships are for AZ equals 0. But you could imagine what it would be if we were going upwards. And the other one here is that the pressure change as you go tangentially around the bucket doesn't change either. And so that kind of makes sense. If you go to the surface, if you went to the surface here and you went around the surface, around the container, then if this wasn't equal to 0, then what would happen is you'd be climbing up on the surface and all of a sudden you'd get back to the same point you were, but you'd be too high, and so you'd have to drop down. And so you can imagine, this is just saying that as you go around the surface is just a horizontal line. In the center, it's a lower horizontal circle. At the edge, it's a higher horizontal circle around the circumference, but it merely has to be a circle of constant height. And that's really just coming out of this expression here. And so the basic expression that we end up getting is this, just as before, from this. It's a bit more complicated now, because now what we'd like to get is a magnitude. What we'd like to get is the slope of this surface, right? And we can get that because we have both the change in elevation that occurs as a function of radius. And so if we think of this surface here, clearly this is just equal to dr and dz. So we can rearrange it just like we did before to get it in terms of this elevation. We can note that the unit weight here is equal to density times gravity, and so we get rid of this term, and this term just becomes g. And so we end up with the expression that the elevation change of the surface is equal to the rotation speed squared, gravity, and the radius. So in the middle, it says that this elevation here in the middle is flat, right? dz dr is 0, means this is horizontal. And as you go progressively further outwards, then as you increase radius, then it gets higher. It's 0 here for the radius. This is r equals 0 in the middle. This is the rotation axis. And as you go further outwards, it increases. And so it's not quite as easy as before, because now it changes with location. And before, in the linear acceleration, it was just a constant. And so if you know what it is at this point, then you know that you can just project up here to get the magnitude very straightforwardly. But we need to be able to, if we want to see what the surface looks like, we have to split this expression up and integrate it. And if we do that, we end up with the one expression that you might need is this. So let me just zip back onto this first page, because I know it's going to not confuse you, but if you look on this first page, you'll see a couple of things. One is this. We've derived and used this. The other ones are these two outcomes. This is the one we just have. So, which is this. And the other thing that we can do is we could also take the magnitudes of the fluid pressures here and this term, and we could use that to be able to integrate it to get the pressure distribution in the system, which is this term here. And so these are kind of standard results. They're obtained in exactly the same way as we did it for the linear case to get two things. One, in the linear case, we want to know the inclination of the free surface. It was a plane, horizontal plane, that reacts to accelerating. It goes up at the back as we accelerate in the other direction. Here it doesn't happen to be a plane, it happens to be kind of parabolic. It varies as 1 over r squared. And as we go down the fluid pressure in that, we see that the fluid pressure varies in two ways. As we go up or down in the fluid, it just varies as we're in a swimming pool. And that makes sense because we said in this case the vertical acceleration is 0. We're not accelerating upwards, we're just static, and we're spinning around an axis. So that kind of makes sense. And as we go out horizontally from the middle of the container outwards, some distance r, then the pressure changes with r squared. So in other words, we start off at some location, a meter out, the pressure is something. If we go out 2 meters, then it's that squared. If we go out 4 meters, it's that squared. And it's proportional to the rotation rate. Okay. So these are two standard results that we can use. And perhaps it's useful to be able to solve a problem with them. Accept them as they are, not as they is, and solve a problem. I think this is an interesting problem. So here's the idea. So we have a manometer U-tube that's filled with something. It's filled with water in this particular case. And I said before, if I had a piece of Tygon tubing, actually I've done it in this classroom, have a piece of Tygon tubing, put it in a water bottle, prime it by filling it with water, and then if you spin it, it'll shower you with water and you'll get wet. That's basically the principle of a centrifugal pump. And so the idea is to be able to suck it out of the Tygon tube, it must have a pressure that's low at the center of the tube that's pulling it out, because at the end of the tube where the fluid is, it has to be physically at atmospheric pressure. That's what we're feeling around here. So as you go along it, it has to be less than atmospheric pressure, because we know from this previous expression we had that pressure decreases as you go in towards the center of rotation. And so this example is basically exploiting that idea. It says that if you spin this tube, what happens to the pressure here? You can imagine that at this point here, in the same way as spinning the tube horizontally, it's going to try and be in tension. And so if the tension is enough that it cavitates, boils just due to a pressure change, but not due to a temperature change, then you'll get an air bubble forming here. It's one way that you can de-air water is by putting stuff in a siphon, taking it up. How many meters would it be? Well, it's 10 meters, right? 30 feet. Take it up over the top of the siphon and back down the other side. Atmospheric pressure here, almost a vacuum at the top, and it takes all of the air out of it into a bubble, and you can collect it. But I digress. So the idea is if you take a U-tube, partially filled with water, rotates around the axis, what angular velocity, omega, do you have to move it at before it vaporizes? And so because the expressions that we have, the integrated expressions that we have a constant in them, we don't know exactly what this constant is. So what we have to do is be able to anchor it to some place where we know the magnitude of that constant. We know here that the pressure equals atmospheric. Right? We know that that radius is at 4 inches. And we know that the rotation speed is going to be omega. We don't know what that is yet. And so what we could do is we could write this expression that this is atmospheric. This is 4 inches squared. This is the density of water. It's in English units, so it's 62.4 pounds, or whatever it is. And that this elevation here, if we take this as being z equals 0, then this elevation here would be equal to 12 inches. Right? So we know this, we know this, we know this, we can assume this, and the only thing we don't know is the constant. So it's like when you integrate things, you can either integrate between limits, in which you don't need a constant, or you can integrate it without limits, in which case you end up with a constant. It's the same process. So if we solve for this, we can get the magnitude of the constant, and apparently it's equal to this. It's a function of rotation speed, which we don't know, and the properties of the fluid, density, unit weight and density. So we have that. So that has anchored our magnitude of the constant, which we now know. And so if now we know what the value of this constant is, we can take this and now we can apply it to somewhere where we want to know the pressure. And so now we'd like to know the pressure here. We know the constant. We know the elevation of that point is going to be 0. You can come in if you want. We know the radius of that point is also going to be 0. We still don't know this, but we do know what this is. So I said that we don't know it, but of course we do, because we know that this magnitude will be the vapor pressure of water in terms of gauge pressure. And so the vapor pressure of the water is going to be P atmospheric, PV minus P atmospheric. Right? So the vapor pressure of water is a small number. I don't know what it is in English units, but you could think of it almost as being 0. And the atmospheric pressure is going to be 14.3 or so psi. And if you 14.7 psi, and if you substitute for this, you can solve for the magnitude of the rotation speed. So merely a consequence of the idea that if you rotate something, you can anchor its pressure somewhere, and if you know that pressure, you can solve for the magnitude of the pressure somewhere else in the system. Just like we've been doing static columns for the last week or so. All right, I'll stop there. So next time we'll start talking about Bernoulli. Now is an auspicious time because 4.1 is the last stuff that's on the midterm.